Okay, finally we have come to the last section of ring theory in this book, section 3.11, polynomial rings over commutative rings. We have already developed the theory of polynomial rings, I mean at least the elementary theory, where the coefficients of the polynomials we are considering are coming from some field. However, this can now be generalized by dropping the field requirement, and in place of a field by considering a general commutative ring. So let us see what some of the beginning lines say. In defining the polynomial ring in one variable over a field f, which we have already done, no essential use was made of the fact that f was a field. In the definition itself, although we have stated the definition by considering a field, actually in the definition all we used was the fact that f was a commutative ring. The field nature of f only made itself felt when we proved that this polynomial ring is a Euclidean ring. If you go back to that result which says that that is the division algorithm, if any polynomial here is divided by a non-zero polynomial, then there is a quotient and a remainder, where the remainder is either the zero polynomial or its degree is smaller than the degree of the divisor polynomial. In that result, in its proof, we had to use the fact that f is a field. There only we needed the full hypothesis that our ring is actually a field. Other than that, we don't need the field nature of our ring from where the coefficients are coming. So why not generalize the situation by dropping the requirement that f is a field and replacing it with some commutative ring? This we can done, and this is what we are going to do now. So we can imitate what we did with fields for more general rings, but this type of conclusions can no longer be true. I mean, they are not necessarily true. So that's why the author says, while some properties may be lost, such as Euclideanism, we shall see that enough remain to lead us to interesting results. So let us see what this section offers. It starts like this. Let R be a commutative ring with unit element. So the only thing that is not necessarily true in R is that every non-zero element may not have multiplicative inverse. So it is one axiom away from being a field. It is a commutative ring and it has a unit element. Oh, but there is one more thing. R now is allowed to be the zero ring, because in the zero ring the only element is the zero element and it is also the unit element. In a field this cannot happen. In a field the unit element has to be different from the zero element, because a field by definition is a ring in which the non-zero elements form a commutative group under multiplication. So for the non-zero elements to form a group, first of all there should be non-zero elements. The set of all non-zero elements should not be empty, and that is why there is something else other than the zero element, and since that part should form a group under multiplication, it must have its own identity, which is the unit element. So this zero element and unit element should be different in a field, which is not necessary in this type of rings. Okay, now by the polynomial ring, in X in the indeterminate X over this ring R, we mean the set of all symbols symbols are just like before. Where these coefficients are now coming from R, and saying that simply this set of symbols is a ring is meaningless. We also have to say what the criterion for equality of such symbols is, what is the addition, what is the multiplication, those things have to be said. So that's why we say and where equality, addition and multiplication are exactly like what we did in section 3.9. Exactly like they were defined in section 3.9. Just like in section 3.9, this system is a commutative ring with unit element. And the notation is also like before. We denote the polynomial ring in X over R by this symbol Rx. Okay, so R is a commutative ring with unit element, and Rx defined exactly like how we defined Fx is again a commutative ring with unit element. But now we cannot claim that Rx is a Euclidean ring. Okay. Now what we are going to, you can see one thing, and this is the type of thing that mathematicians look for. Namely, they start with something and they discover something bigger but of the same type. we start with a commutative ring with unit element, we get a bigger commutative ring with unit element. So now we can use this one and form yet another one and keep on doing this any finite number of times, and if we do that we get polynomial ring in several variables. We now define the ring of polynomials in n variables. x1, x2, etc. up to xn. Just like x is an indeterminate here, these are also independent indeterminates. Okay, there is no relationship between these indeterminates. Let R be a commutative ring with unit element. We define some ink is needed. We define the polynomial ring in these variables over R. Denoted by, if you want you can write x2 also, it does not matter, it does not change the notation, as follows. R1, we do it in a sort of recursive way, we do it in steps. R1 is, let's call the first polynomial ring, which is the ordinary polynomial ring in one variable x1 over R, let's call that R1. Since this is also a commutative ring with unit element, we can then define R2 to be the polynomial ring in x2 over R1, and we can continue this process. Finally defining this to be Rn, which itself is the polynomial ring in the variable xn over Rn minus 1. So you can see that the way we have defined this is actually quite complicated if you really think about it. Say you have some ring R, a commutative ring with unit element, and suppose by this scheme we want to define this polynomial ring. First of all, we will define Rx1 and then, considering this as a commutative ring with unit element, which it is, we form the polynomial ring in x2 over this, and then this is also a commutative ring with unit element, so you form the polynomial ring in x3 over this ring. How would an element in this final ring look like? Okay, since this final ring is a polynomial ring in x3 where the coefficients are coming from here, so such an element will look like this. We are taking an example, say x3 cube plus 1 constant. So here I will take an element from this ring, and here also as a coefficient of x3 cube I will take an element from this ring. Okay, now that element is itself a polynomial in x2. Fine, so I can take that polynomial like this. Say this is x2 multiplied by something, and that something is coming from here because the coefficients of this polynomial in x2 that I am going to write now are coming from Rx1, so they themselves are polynomials in x1. So that polynomial itself can be 3x1 cube plus 2. Say I should not have written 3x1 plus 2. For the sake of definiteness, let us consider the ring of integers here. Instead of taking an arbitrary commutative ring with unit element, let's take the ring of integers. So then I can of course write 3x1 plus 2. Then this is a polynomial in x1 over z. If I multiply that with x2, then this one becomes a polynomial in x2 over zx1. I multiply that with x3 cube and plus, now I am going to write something else. So this one can be written as, say, x2 cube plus 3x1 x2. Okay, so this is an element in this ring where the coefficients of the powers of x3 are polynomials here, and they themselves are polynomials over this. So each one of them has coefficients in this polynomial ring. So you can see that the things will become more and more complicated as the number of variables increases. However, if you forget about all these things, that which coefficients are coming from which field, and you start doing school level algebra without any care for what is happening, then you can simplify the situation. We will come to it later, come to the issue of whether this can be done or not. What I am trying to say here is that you just simplify the expression as if these are just real numbers. Then we will get 3x1 cube x2 x3 cube plus 2x2 x3 cube plus x2 cube plus 3x1 x2. Okay, now this is an expression where we have terms which look like this: ai x1 to the power i1, x2 to the power i2, x3 to the power i3, and it's a sum of such terms, finitely many such terms, where these ai's are actually integers coming from the original ring from where everything started. This 3, this 2, 1 is here, 3 is here. They are integers, and along with that, terms which look like this, which are not powers of any one variable. They are products of powers of all the three variables. You can consider, you can think of x1 being present here in this form, x1 0, x1 to the power 0. Like that, here we have x1 0 and x3 0. Here we have x3 0. Okay. Now, if someone simplifies every such complicated polynomial like this, and then in the resulting system, where instead of considering such convoluted and complicated expressions, we consider an expression where the things look like this. We have a coefficient here that is coming from the original ring R, and along with that we have symbols that look like this, where this I1, I2, I3, In, these are, each one of them is a non-negative integer. Then with these expressions we can calculate, we can add two such expressions, we can multiply such expressions. How shall we add two of them? That is quite easy. You just add as if you are adding two algebraic expressions. If you get like terms, you add their coefficients. If you get another term in another such polynomial where you have x1 cube, x2 and x3 cube, you then add their coefficients, and that will give you one term in the sum of those two polynomials. And if you don't get like terms, then you just write the sum the way it is. That is also a finite sum of such terms. So that ultimately gives us one such expression, one such multivariate polynomial. A polynomial where the coefficients are of course there, they are coming from the base ring from where things are being taken, that is the actual coefficients are being taken, and instead of having one variable, you have powers of several variables in every term. Like that, addition can be handled. What about multiplication? If you just simply multiply two such expressions as if you are doing ordinary algebra, then you may encounter some other terms. Say in another such expression you may encounter this. Now if you multiply this term with this term, then the rule is that the exponent of x1 will now become 7, as if we are using rules of exponent, treating this x1 as a real number. In that way, if you multiply and you use the distributive law, then one can show that with that addition and multiplication, you will again get a ring, which turns out to be actually isomorphic to this ring, the ring that we have defined like this in this complicated way. This, however, is not easy to show, but we will have to show it and we will show it in the exercises. Although nothing has been said about it, the author has simply said that, simply assumed, he has not even mentioned that this isomorphism is there between such expressions and this type of expressions. Okay, however, we will not simply assume that we are actually going to prove that, but that will be done in the exercises. So you see, right after defining this, the author writes this. The proof that these two things are isomorphic is going to be somewhat, I won't say complicated, but it involves many strange looking and complicated looking big expressions. That's all. If we carefully go through all the calculations, we will see that the end result is that they are isomorphic. These are the types of things you have to see only once in life, convince yourself and move on. There is no beauty in them. So the author says just this: its elements are, its elements means this multivariate polynomial rings elements. Are of the form summation a I1 I2 etc. In this is a multi-index. Suffixes are also called indices, right? This multi-index keeps track of the fact that this coefficient appears as the coefficient of this term. Okay, because in one such term we have all these numbers. Now it's not enough to say that this is the coefficient of x1 to the power I1, because you may have several other terms also which may have I1 as the exponent of x1, and here you may have something else entirely. These integers may be different from these integers. So this is another term where I1 appears. So you cannot say that here also the coefficient is ai1, because then you won't be able to distinguish between these two coefficients. So you need the full information of where it is occurring. So that's why a multi-index. This is not the product of I1, I2, etc. Okay. If this is confusing, you can put commas in between them, or you can even write it as a vector like this. But we can understand from context, because we will not be using too many such expressions where we have to use multi-index. So Herstein simply says that the elements in this look like this. Literally that is not true. Literally that is not true, but if you assume that isomorphism, then of course it can be considered. I mean, you can identify this element with another element that has come from here using that simplification method, multiplying everything out and then taking everything outside, where I1, I2 belongs to R, and where addition where this belongs to R, we can write like this. Addition and equality are defined component wise. That means if you encounter two such expressions, then they will represent the same polynomial if and only if the corresponding coefficients are equal. So component wise equality defines equality between two such polynomials, and addition also has to be done component wise. If you add two such polynomials, then you have to add the like coefficients, that is the coefficients that appear for the same term in both the polynomials. They have to be added together. So that's what we mean by component wise addition. However, multiplication, it's a little difficult to describe, and where multiplication is defined by or done by same thing, by using the distributive law and the rule of exponents. When I first encountered this section, this issue of the author just simply saying that the elements in this in this ring are this, I was not able to resolve this issue because actually it is not true. But I immediately understood there is some isomorphism, but to prove that such an isomorphism exists it did not come to my mind how to accomplish that. So only after I was able to do that was I put at ease with this whole thing. So the last section tortured me for quite a long time. And the rule of exponents, this rule, if you multiply two such terms, J1 J1 I2 plus J2 In plus Jn. Just to show you what this really means, I mean equality and addition you understood, but the multiplication, what is the exact meaning of these lines? To see that, let us multiply two such terms. Suppose over the ring of integers, 3x1 x2 xn, say, where all these superfixes are 1 minus 4x1 4. This polynomial and say x1 x3 x5 minus the rule that they have described here says that we have to use the distributive law. That means in carrying out this multiplication, and in fact this is the definition of this multiplication, you have to do the calculation as if you were using the distributive law. So that means you have to multiply this term with this term. If you do that, assuming that n is actually greater than or equal to 5, the result will be this. Then you multiply this one with this one. That will give you then minus 4 x1 to the power 4. I am writing this products separately, there is a reason. And finally plus 4x1 to the power 4 times this. Distributive law tells us only this much. After that, we need more definition to carry out the product completely, and that rule is this. The meaning of this product is this. That's the definition. So according to that meaning, this will be and then oh sorry, I think I wrote this one wrongly, excuse me. x1 square x2 x3 square, here we have x3 and x5, okay, so x4 x5 square x6, then after that we will have xn. So this is this term, the first one. Then in the second one we have all squares. Then in the third one, minus 4 x1 to the power 5 x3 x5, and finally plus 4 x1 to the power 5 x2 x3 up to xn. So this is the definition, and using the definition, if we multiply these two, for example, then we get this, again such an expression. Now with this definition of multiplication and with component wise addition and equality, the set of such symbols also forms a commutative ring with unit element, which we will show is isomorphic to the multivariate polynomial ring that we have defined. Okay. Now of particular interest, to us is the case r equal to f, where f is a field. If we have only one variable and if we are starting with a field, we won't get anything new. We will again get such a polynomial ring, which is a Euclidean ring. We have seen all those things. However, even when the base ring is a field, if the number of variables increases and it becomes more than one, then the nature of the polynomial ring changes completely. Here we obtain this. The polynomial ring in n variables over the field f. This ring is quite important in many places. Okay, now we have just simply mentioned that these rings, these very general type of polynomial rings where even there is not just one variable but there may be many variables, more than one, they will lose some of the properties of our familiar polynomial ring. But there are enough interesting properties to be studied, and in particular we will be interested in knowing how the structure of the base ring is affecting the structure of this. That is, if we have already assumed the base ring to be a commutative ring with unit element, this then again is a commutative ring with unit element. But what more is true? If we assume this to be an integral domain, will it follow from that this is also an integral domain? So such questions will be investigated. And in this direction we are going to look at the first result. If R is an integral domain, then so is Rx. There is an advantage of that recursive type of definition for the multivariate polynomial ring, because if you prove this kind of result, then you can apply it again and again a finite number of times to conclude that a multivariate polynomial ring also has that property. Namely, you can clearly see once you prove this result, then it means this is integral domain. So if you add another variable, that corresponding polynomial ring will also be an integral domain, and this will continue for any finite number of variables. The proof is not very difficult. In fact, it's almost like the proof we had of the fact that this is an integral domain where f is a field. For a non-zero polynomial in Rx, where am is not equal to 0. I think okay, we can call this something. We can give it a name, fx or something like that. A0 plus a1x plus we define the degree of fx to be m. You may wonder why are we again defining degree? We are again defining degree because we did this for polynomials where the coefficients came from a field. That is a special situation. Here the coefficients are coming from a general ring. So that's why it is in a sense a repetition. So that is the price we pay for taking this path, that is starting from polynomials over a field and then generalizing the results as far as they can be generalized to polynomials over commutative rings with unit element, because this path is more natural. You familiarize yourself with polynomials over fields, and then with the experience you gained about these things, you can quickly generalize. However, one can also, in the beginning itself, one can study this type of structures where R is a commutative ring with unit element, and then one can consider the special case where R is a field. Had this been done, we would have had to define degrees and other things only once. But we are not doing that because that path to come from here to here is extremely unnatural. To tell you in the beginning itself something like this is quite unnatural because this is extremely general. It's better to go for the sake of understanding from concrete to abstract rather than from abstract to concrete. But the price we pay is a sort of repetition. So the degree to be m, that is the degree of fx is the index of the highest non-zero coefficient. And this definition of degree is nothing different from what we already defined for polynomials over fields. Okay. Now one can prove that for non-zero elements fx and gx in Rx, the degree of their product, again same result we previously had, is the sum of the I did not mention that we will be denoting degree by DEG. You can add one small part here, DEG f of x, comma, that is degree of f of x is denoted by that symbol, that notation. and this we have to actually do in exercise 3. Now, do you notice one thing about this result? It is given that fx and gx are two non-zero polynomials in this polynomial ring, okay, and we are stating that such a formula is true. According to our definition here also, just like that field case, degree is defined only for non-zero polynomials. So the fact that this formula has to be proved also means that the polynomial fx gx should be non-zero, because then only its degree will make sense. So it's a part of this result that the product of two non-zero polynomials is a non-zero polynomial. In particular, this means that fx gx is also not equal to 0. So you have taken two non-zero elements in Rx and their product is also non-zero. So that means there is no zero divisor. Thus Rx is an integral domain. And now we can make use of this immediately using the above lemma repeatedly. We get the following result. Corollary. If R is an integral domain, then so is this n-variable polynomial ring. Okay, R is an integral domain, so Rx1 is an integral domain. You add one more variable that will also be an integral domain, and it continues like that. So you get the nice result, which if you think about it actually looks quite complicated. If you multiply two very complicated looking polynomials here, which both of them are non-zero, then their product will be non-zero. In particular, for a field F, since every field is an integral domain, so we can particularize this result, this corollary, for a field. This is an integral domain. And as such, it has a field of quotients. Recall in one previous section we proved that every integral domain can be embedded inside a large field, namely its field of quotients. Large in the sense that it contains the integral domain, just like the integral domain of integers can be embedded in its field of quotients, which literally is field of quotients of integers, because quotients of integers are defined as rational numbers. So like that, this particular integral domain also has its own field of quotients. This field is known as the field of rational functions in these variables over f, and this field also has a notation and is denoted by this symbol. Okay, instead of using square brackets we use round brackets. This field plays a major role in algebraic geometry. This area of mathematics is quite fascinating. It's also extremely deep. Some of the deepest results in mathematics are present here in algebraic geometry. We actually come across algebraic geometry quite early in our mathematical education, because you see we come across things like this. We learned that geometrical figures have equations attached to them. Algebraic geometry is the study of geometry using algebra, just like differential geometry is the study of geometry using differential calculus or analysis. Like that, we use algebra to study algebraic geometry. That's the vague definition, but it's an extremely vast subject. It has many parts within it which themselves are quite vast subjects, and there are several levels of abstraction in this subject. So there this type of fields, and in fact this type of rings become important there. You can, I think, see why. This is a polynomial in two variables. If you forget about equal to 1, this expression x square plus y square is a polynomial in two variables. So this expression is an element in this polynomial ring, and the properties of this ring tell us many things about such expressions and the geometric figures that they represent. It's a very interesting subject. I don't know much about this subject myself. I have plans of studying it. for us, we will also use this particular field of rational functions in our study of Galois theory in chapter 5, where we treat extensions of fields. Importance in our study of Galois theory in chapter 5, named after Évariste Galois, the brilliant mathematician because of whom people came to know exactly why we don't have formulas for finding the roots of a polynomial equation where the degree of the polynomial is at least 5. We have formulas for, linear equation, of course. Linear equations, if you think about them, they can be immediately solved, provided that the equation is linear, that is, this A is non-zero. Okay. For quadratic equations, you almost know the formula by heart. Minus b plus minus square root of b square minus 4c. In fact, most of us memorized this formula in school. For cubic equations also, there is a much more complicated, but nevertheless, a formula is there that tells us about the roots, and that formula, you can see that in every case the formula for the roots is involving the coefficients of the equation. And for a biquadratic equation, a polynomial equation of degree 4, even that also has a formula, but starting from the 5th degree, the equations have no formulas that can be expressed in terms of the coefficients of the equation. The lack of such formulas was proved, and he understood, this mathematician, why such a thing is impossible. By associating with such an equation a group of symmetries of the roots of such an equation, and by associating with such groups fields and doing something, okay, with the help of that association, he was able to show that equations of degree at least 5, they lack formulas for their roots in terms of the coefficients. So that is Galois theory. Just like that Galois theory, in fact, there is I think a differential Galois theory also, where a parallel theory is there that tells us about not ordinary polynomial equations but differential equations. So many things are there. Okay, there are many more things in this section that we will see. I think it's better to stop the video here, and we will continue in the next video. So many things are there to study, but life is so short. So that will be all for tonight. If you find these things interesting, please consider subscribing. That means if you are new to this channel and if you haven't subscribed. So that's it. This is me, Lucifer, from a mathematical room. Have a nice night.